So for the last piece, I would like to prove Euler's identity. Okay. So remember, Euler's identity is e to the j theta equals cosine theta plus j sine theta. And we'll take theta typically in the interval minus pi to pi, j squared minus 1. All right. So for the first step, we need to actually define what we mean by e to the j theta. So for starters, I'll just say e is a real number, and we'll just say it's to be determined. Right now, let's suppose we forgot how it's defined, and we don't know how to define it, because we will learn, this proof will define it for us. This proof will tell us how we need to define it to make it true. But we just insist that it's a finite real number. And then, what do we mean by e to the j theta? So I assume everybody knows what we mean by e to the x. Okay, e to the x is a real valued function. It maps the real line to the real line. And so I'm assuming there's no problem there. We all know what exponents are, and real number raised to a real power is no big deal. I actually, in the book, go through the details of that, starting with integer exponents. And integer exponents, squaring, cubing, that's just iterated multiplication, right? And then it extends that to rational exponents, and then finally real exponents. And so if you really want to see the whole story, all the way from integer exponents, you can read that in the chapter. But I'm going to start here, assuming that we're okay with real exponents. Then what do we do for imaginary exponents? And the answer is we need the power series expansion. We need the Taylor series expansion. We need to basically expand this function as a polynomial in x, because polynomials are well defined. Polynomials are just of the form, let me write it down and then say that. So we have, we need the series expansion of e to the x. And in general, the series expansion of f of x has the form f0 plus f1x plus f2x squared plus dot dot dot. And we'll go out to some, we may go out to some finite number of terms and then have a remainder term. And so it's basically just a polynomial. And you can see that polynomials are well defined. So if I want to look at now what f of jx is, it's obviously f0 plus f1jx plus f2jx squared. And so all we have is multiplication going on, multiplication and addition. So it has an obvious generalization to the complex case. So that's why we want to go from some real function to its power series, where we then can plug in an imaginary argument or a complex argument, and then that's a well-defined extension. So what we need is the expansion of e to the x. So I'll just say note that in this formula, this polynomial formula, we have that f of 0 obviously equals f0, right? Because if you set x equal to 0, then all of the terms, all the higher order terms go to 0, and you're left with the constant term, f0. And then similarly, if we differentiate it, let me just say the first derivative of x, I'm assuming everyone can differentiate a polynomial. This is about the only calculus we're going to need. But you differentiate a polynomial, the constant term goes away, the linear term becomes f1, then you have 2f2x plus 3f3x squared, and so on. So that's just the rule for differentiating a polynomial. If you want to, if you want to see that derived, we can do that in office hours. And then more generally, the kth derivative of x evaluated at 0. Well, let me look at the kth derivative of x. It's going to be, you can see it generalizing from here. It's going to be k factorial. Yeah, I want to take this at x equals 0. All right, so let me start this over and say f of 0 equals f0, f prime of 0 equals f1. So you can see that up here that so I derived the first derivative of the polynomial, and then I set its argument to 0, and that will annihilate all terms that have x in them. And so it'll leave me with f1. So f prime of 0 is f1. And then f double prime of, the second derivative of the polynomial evaluated at 0 is 2f2. And in general, the kth derivative of this polynomial expansion evaluated at x equals 0 is k factorial times f sub k. So this gives us the formula for f sub k, the coefficient of the polynomial. It's basically just the kth derivative of the function we're expanding evaluated at 0 divided by k factorial. Now, of course, that assumes the function is differentiable. You have to be able to differentiate it. And it has to be differentiable everywhere from 0 to where you're trying to evaluate it, because we're using the derivatives at 0, and we're extrapolating the function from there as a polynomial expansion. And we say that we're expanding about the point x equals 0 here. And that's actually called a Maclaurin series, if you want to get the historical name for that. And it's a special case of Taylor series. So I'll just say it's the Taylor series about x equals 0. So the Taylor series will allow you to expand about any point x sub 0, let's say. And then if you do the expansion about 0, then you get to call it a Maclaurin series. These are just names, but you'll see them around. Okay, so now we have an expression for our general continuous differentiable function. F of x can be expressed as f0, the constant term, plus f prime of 0. Yeah, actually that's not, we just solved for f0 as f of 0. And then it's f prime of 0 times x plus 1 over 2 factorial f double prime of 0 times x squared, and so on. All right, so now we have our polynomial. This is our Taylor series expansion, our Maclaurin series expansion. It's our polynomial expansion. It's our series expansion. These are all the terms you can use for it. It's a polynomial expansion of this function. All right, so now what we want is the series expansion of e to the x. So we need the series expansion of f of x equals e to the x. All right. Now, we have f of 0. That's easy, right? Because f of 0 is just e to the 0, which is 1. E is some real number. We can say that it's greater than, we're going to make it be greater than 0. It's a real number greater than 0. And that means that e to the 0 will definitely be 1. But what about f prime? What is f prime of x? Well, by definition, that's the first derivative. So that is the limit, as delta goes to 0, of f of x plus delta minus f of x over delta. And we can plug in now f of x equals e to the x and see that it's the limit, as delta goes to 0, of e to the x plus delta minus e to the x over delta. So using properties of exponents, we can factor e to the x out of all this. We can say that's equal to e to the x times the limit as delta goes to 0 of e to the delta minus 1 over delta. And I can write this out more explicitly by saying the derivative with respect to x of e to the x we derived is equal to e to the x times the limit as delta goes to 0 of e to the delta minus 1 over delta. So then, this gives us a really good idea for what to define e as. Because, so we want to define e so that this limit is 1. So that's we're going to spend our e chips on this. So define e such that, I mean, we have to make sure that it works, that nothing blows up, nothing's, infinity and so on. So define e such that the limit as delta goes to 0 of e to the delta minus 1 over delta equals 1. And then that will imply that derivative with respect to x, e to the x, equals e to the x. E to the x is its own derivative. Well then, say we do that, then what is e? Let's see what e has to be to make that true. Well, we're saying that for this to be true, then we can, let me just say it like this. E to the delta minus 1 over delta goes to 1 as delta goes to 0, which implies, which is true if and only if, I'll say, e to the delta minus 1 goes to delta as delta goes to 0, or e to the delta goes to 1 plus delta as delta goes to 0, or e goes to 1 plus delta to the 1 over delta as delta goes to 0, or setting delta being defined as 1 over n, to get back to our previous definition, e approaches 1 plus 1 over n to the n as n goes to infinity. That was the way we defined it originally. And I'm using this sort of breezy notation that means e is defined as the limit as n goes to infinity of 1 plus 1 over n to the n. It's just saying the same thing in a more compact notation that's more easy to manipulate and calculate with. So then we have to check that this is, we have to check that it's finite. And so, you try n equals 0, 1, 2, 3, 4, 5, and see what it does. And sure enough, it starts out at 1 and it goes up to, so let's say that's 1, here's 2, and here's 3. So there's some asymptote here, 2.71828. So e is up here, and you'll see that it sure enough approaches this asymptote. So then you have the issue of proving convergence, but it works out. It does converge to a constant, and it's just one constant for all problems. So it's a universal constant e, and this is where it comes from. Another way of saying it is that if you think about the function a to the x, just some real number to the x power, and take its derivative, you'll get a log a coefficient, and if you choose a to be e, then it goes away. Another way of saying that, because the natural log of e is 1. So it's just a way of getting rid of the external constant. That's why it's fun to know. And now I'll just mention in passing that it also means that e to the x equals the integral e to the x, which is, if you remember integration, That's kind of surprising, right? Because integration is the area under a curve. And so it might be a little bit surprising that if you integrate, that the area under the curve is the same number as the value of the curve. That might be a little surprising. Well, yeah, there's a constant integration there. But it's a good example of why, so the internet is exploding exponentially, right? And so it means that the cost of storing the internet is comparable to the cost of storing all of the internet for all time. So if you look at like the Wayback Machine, archive.org, there's these websites that attempt to record everything that's ever been on the web. It's not that much more expensive than just the web itself. So you can have all of the web for all time for about the same cost as you can have today's web. That's because the integral of e to the x is e to the x. They're both just going up exponentially. So let's hear it for the Wayback Machine. Okay, so now we have the derivative of e to the x. So now we can take the series expansion and prove Euler's identity with that. All right, so what do we need? So we have f of x equals e to the x, which equals f of 0 plus f prime of 0, x plus f double prime at 0, x squared over 2 factorial plus dot dot dot. Let me go ahead and put the kth term in there. F kth derivative at 0 over k factorial times x to the k. Just to remind you of that general term in there. And off it goes. So now, this is the easiest series expansion you'll ever see, right? Because every single derivative is e to the x. Because if you differentiate e to the x and get e to the x for your first derivative, well, guess what? The second derivative is also e to the x, and so is the third derivative. So it's just e to the x is everywhere. So e to the x is, what is e to the 0? It's 1, plus e to the x at 0 again, which is 1, so 1 plus x, plus x squared over 2, 2 factorial to be formally nice. Then we have x cubed over 3 factorial plus dot dot dot. General term being xk over k factorial. Let's put a dividing line here. So that's it. That is the simplest series expansion. I suppose if you had a function that the successive derivatives brought a factorial out, then you can make a nicer expansion, but that one's going to diverge. So I think this is the simplest series expansion you're ever going to see. So now we have e to the x as a polynomial. So now we can plug in complex numbers into the polynomial, and that defines e to the x for a complex x. So define e to the j theta as 1 plus j theta plus j theta squared over 2 factorial plus j theta cubed over 3 factorial and so on. And that is our definition of e to the j theta. We're just plugging into the polynomial series expansion of e to the x. Can't be anything else. And one thing we can notice is that the even exponents are going to give us real numbers. So j theta to any even integer is going to be real. And j theta to any odd integer is going to be imaginary. So we can split this into its real and imaginary parts. So we can first write out, let's say, the real part. So the real part will start out with 1 minus theta squared over 2. Then there'll be a plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial, and so on. And then we'll have the imaginary part, which is all the odd order powers of theta, So we'll have, I'll just factor j out, and then we'll have theta. Then we'll have a minus theta cubed over 3 factorial. And we have an alternating series because j to the n has a period of 4. Maybe I should mention that off on the side. J to the n equals 1, j, minus 1, minus j, repeat. This is a little side bubble here. And then we have theta to the 5 over 5 factorial. All right, so that's the form of this series expansion. And so if you have, if you know the series expansion for cosine and sine, then you know the answer. So this is how the answer falls out. So basically this is cosine theta plus j sine theta, and that proves Euler's identity. And so to finish it off, we just have to go verify that these are the derivatives of sine and cosine. I'll just say since the nth derivative of I don't want to change to x. The nth derivative of cosine of theta is either minus 1 to the n over 2 for n even over 0 for n odd. And similarly for sine. So why don't we go ahead and show that? Let's go ahead and compute the derivatives. So proof. We have to show this, let's say. So since I have the time. I didn't think I'd have the time. I was just going to say, you all know the series expansion for sine and cosine. Not that you necessarily remember it. But it's a more straightforward thing because we're dealing with trig functions. And so I can assume that everybody's seen some trig. All right, so let's look at the derivative of cosine. So the derivative with respect to x of cosine of x is defined as the limit, as delta goes to 0, of cosine of x plus delta minus cosine of x over delta. Okay, that's just the definition of derivative. And so here's where we need a little trig. We have to remember the sum of angles formula, and so cosine of x plus delta is cosine of x times cosine of delta minus sine of x sine of delta. So now, I'm assuming you know some double angle formula. This you can show by basic geometry. You can derive the sum of angles formula just with a stick in the sand like the Greeks did it. So cosine of delta, as delta approaches 0, goes to 1. Okay, and that means we're going to get a cancellation of the cosines from that. Now sine of theta, it approaches 0 as delta goes to 0, but before it becomes 0, it becomes delta. So sine of x equals x for small x. And we're going to need that because the cosines have canceled. And we can't replace sine of delta by 0 because we're dividing by delta. So this is a tricky limit. You have to be careful. So you replace sine of delta by delta, and then you get a cancellation of delta in the numerator and the denominator, and what's left is minus sine of x. And this is something you probably remember. So you probably remember that the derivative of cosine is minus sine. Thank you. So you can sort of see it too. If you plot cosine, you can see that its derivative starts out at 0. The slope is 0. And sine starts out at 0. And then as you go forward, the slope becomes negative. And when you reach a zero crossing, you get a maximum slope. And so if you know the derivatives of sines and cosines or sines and cosines, then this graphical inspection will remind you that, oh yeah, it's minus sine, that's the derivative of cosine. You know, the slope starts at 0 and then it goes negative. And so let's just do sine. So the derivative with respect to x of sine of x is by definition the limit as delta goes to 0 of sine of x plus delta minus sine of x over delta. And now we need the sum of angles formula for sine, which is sine of x times cosine of delta plus sine of delta cosine of x. Does everybody remember that? That hopefully rings a bell. So cosine of a plus b is cosine a cosine b minus sine a sine b, and sine of a plus b is cosine a sine of a plus cosine of b sine of a, or flipped. All right, so that is the formula. Now, as delta goes to 0, cosine of delta is going to go to 1, and we're going to cancel the signs. Sine of delta is again going to become delta. And that delta is going to cancel the delta down below. And we're going to be left with cosine. So the derivative of sine of x is cosine of x. And you can plot that and see it as well. So it starts out maximum, like cosine, and then it goes to 0. So it reaches 0 here, 0 slope. All right, so now we've got the derivatives of sine and cosine. And now you just have to plug in for x equals 0 and verify the terms in the Taylor expansion for sine. So I think everybody can do that, right? Anybody want to see anything? I mean, I could trudge through a little bit more and really grind out every single derivative, and but we would probably just fall asleep, wouldn't we? So who has a question or a comment or a thought or what's next? So what we've shown then is that e to the j theta equals cosine theta plus j sine theta. And the way that we showed it was by taking a Taylor expansion of e to the x, defining e to the j theta as that expansion polynomial evaluated at j theta, and showed that it broke into a real part and an imaginary part that consisted of the polynomial expansions of cosine and sine, respectively. So there it is. That's how you show it. And it's a valuable tool. You'll see it over and over again. It's a really useful thing. Let's see what's coming up. Yeah, so next time I'll talk about nth roots and the roots of unity, and then we'll go on to sinusoids and exponentials, which are fundamental, and start talking about some audio-specific stuff and some audio applications. And then we'll be doing the DFT, the discrete Fourier transform and its theorems. And so, I would classify this as fairly elementary analysis, sort of like advanced high school math right now, and or early college engineering math. And then when we get to the Fourier theorems, it'll still be made out of that, but experience tells me that it's a little, it's up a level. Maybe just because it's there are all these theorems that are easy to prove using this kind of math, but you have to really internalize them on their own level. In other words, you're trying to build another floor in the building, and so we want to spend a little extra time on the Fourier theorems, and then we'll limit this whole spectrum analysis phase to half the quarter, so that we have the whole other half for the filters, recursive digital filters in their analysis, poles and zeros, frequency response, phase response, and applications. So bring on your questions, comments, desiderata. Also, feel free to say, gee, I wish you would cover X, Y, Z, and I'll try to squeeze it in. I'm going to try to convert these videos tonight. I don't know why they won't be